Hello, welcome to a new physics lesson. Today, what we are going to do is to show how to get to the Cauchy-Riemann equations from polar coordinates from the fact that we know what is the structure of these equations, but in Cartesian coordinates, okay? So we know that for a complex variable c defined as x plus iy, we can define a complex function f of z, which is the sum of two functions of two variables, u of x comma y plus I b of x comma y, right? So yeah, we know that this is the general expression for a complex function that we know that on some region, if it is analytic, I mean that the first derivative exists in that region, then we know that the Cauchy-Riemann equations are satisfied. And these equations are the next. The derivative of u with respect to x is equal to the derivative of b with respect to y, and the derivative of u with respect to y is equal to negative the derivative of b with respect to x. So we know that this is true for this function. And we want to find some equivalent equations, but for the polar coordinates. I mean that u and b are now expressed in terms of r and theta. So this means that u is a function of r and theta, where r is a function of x and y, and theta is a function of x and y. So how can we see this? Well, I think it's convenient to make a quick draw about the situation. So we know that we can locate a point in the complex plane just by giving the real part and the imaginary part. And then we know that we can express this complex number in terms of the magnitude of the the distance from the origin to the point, and then a specific angle, right? So the functional relation between r, theta, x, and y is that r is equal to the square root of x squared plus y squared, and theta is equal to the inverse tangent of y divided by x. Okay, so we are going to start by calculating the derivative with respect to x of u. But now u is a variable of r and theta. Okay, so we can see that as the derivative of u with respect to x equals to the derivative of u with respect to r times the derivative of r with respect to x, and then plus the derivative of u with respect to theta, the derivative of theta with respect to x. This is by using the chain rule, right? Recall that u is now a function of r and theta, which are functions of x and y. Okay, so we are going to be interested in calculating the derivative of r with respect to x and the derivative of theta with respect to x. Okay, so from here, we can do that easily. So for example, the derivative of r with respect to x is going to be, well, 1/2 x squared plus y squared to the negative 1/2, and then 2 times x. So if we simplify quickly, we know that dr dx is equal to x divided by, well, r, right? Because r is the square root of x squared plus y squared. And then from here, we know easily that the derivative of r with respect to y is going to be y divided by r. Okay, and then we are interested in calculating the derivative of theta with respect to y and with respect to x. So the derivative of theta with respect to x, let's say, is going to be, well, looking that we have an inverse tangent, we are going to use the famous formula, which is 1 divided by 1 plus y divided by x squared, and then times the derivative of the argument with respect to x. So that will be minus y divided by x squared. And then if we multiply this x squared by this denominator over here, we will get that this is minus y divided by x squared plus y squared. And then, well, this is r squared, right? So this is minus y divided by r squared. And I leave you as a homework to show that the derivative of theta with respect to y is equal to x divided by r squared. Perfect. So with these results, we can substitute over here to get that the derivative of u with respect to x is equal to the derivative of u with respect to r times the derivative of r with respect to x, which is x divided by r, plus the derivative of u with respect to theta, and then times the derivative of theta with respect to x, which is minus y divided by r squared. So let me take that minus over here, y divided by r squared. Okay, perfect. So I think this is a result that is worth to be circled. And well, we want to use the fact that we know what is the Cauchy-Riemann equation for Cartesian coordinates, and that is satisfied. So that means that, well, we may need to calculate now this derivative over here, right? And then we are going to set them to be equal. So the derivative of b with respect to y is the derivative of b with respect to r, the derivative of r with respect to y, plus the derivative of b with respect to theta, the derivative of theta with respect to y. And this is equal to the derivative of b with respect to r, the derivative of r with respect to y. That is, well, this thing over here, y divided by r, plus the derivative of b with respect to theta, and the derivative of theta with respect to y, which is x divided by r squared. So this is the derivative of b with respect to y. Okay, perfect. So as you should guess, we are going to do the same, but now with the second Cauchy-Riemann equation. We now need to calculate the derivative of u with respect to y. Okay, so the derivative of u with respect to y, the derivative of u, r, y, u, theta, theta, y. This is the derivative of u with respect to r. Well, the derivative of r with respect to y, which is y divided by r, plus the derivative of u with respect to theta, and the derivative of theta with respect to y, which is x divided by r squared. So this is this. Okay, let me circle. And the derivative of u with respect to, the derivative of b with respect to x is the derivative of b with respect to r, x, theta, theta x, okay? So this is the derivative of b with respect to r, and the derivative of r with respect to x, which is x divided by r, plus the derivative of b with respect to theta, and this will be minus, and then y divided by r squared, right? Okay, so this is the derivative of b with respect to x. Let me circle. And then, as we know, we can set these two equations to be equal and these two equations to be equal. So for the first one, we are going to get the derivative of u with respect to r, x divided by r, minus the derivative of u with respect to theta, y divided by r squared, equals to the derivative of b with respect to r, y divided by r, plus the derivative of b with respect to theta, x divided by r squared. And then for the second one, so for the second equation, we are going to get that the derivative of u with respect to r, y divided by r, plus the derivative of u with respect to theta, x divided by r squared, is equal to, and remember that we are going to get the negative of this expression, right? The Cauchy-Riemann equation tells us that, well, we need to take this minus sign over here. Okay, so this will be minus the derivative of b with respect to r, x divided by r, plus the derivative of b with respect to theta, y divided by r squared. And let me label these two equations 1 and 2. So notice something here. What happens if we multiply this equation by y, for example, the second one? We are going to get the derivative of b with respect to r, xy divided by r. And if we multiply by x the first equation, we will get the derivative of b with respect to r, y, x divided by r. And then if we sum them, well, we are going to get that these, for example, two elements are going to cancel. Okay, so I think that will be a good clue to follow. So the first equation is going to be the derivative of u with respect to r, x squared divided by r, minus the derivative of u with respect to theta, xy divided by r squared, equals to the derivative of v with respect to r, xy divided by r, plus the derivative of v with respect to theta, x squared divided by r squared. And the second equation, it's by y. So the derivative of u with respect to r, y squared divided by r, plus the derivative of u with respect to theta, xy divided by r squared, equals to negative the derivative of v with respect to r, xy r, plus the derivative of v with respect to theta, y squared, r squared. So as I mentioned, we are going to sum both equations. And for example, for the first element, we will get the derivative of u with respect to r, x squared plus y squared divided by r. Recall that x squared plus y squared is equal to r squared. So this is r squared. And then r squared divided by r, we will get r. And then if we sum, this will cancel. So this will be equal to, these elements will cancel also. And then this is the derivative of v with respect to theta, x squared plus y squared divided by r squared. And you should know that this is equal to 1. Okay, so I think that with this, we have found the first Cauchy-Riemann equation in polar coordinates. So it's already an important result. Okay, so that was obtained if we sum both equations. But now what happens if we subtract them? Well, that is what we are going to do. So for the first element, we will get the derivative of u with respect to r, x squared minus y squared divided by r. And then it will be minus the derivative of u with respect to theta, 2xy divided by r squared, equals to the derivative of v with respect to r, and then xy minus xy, so that will be 2xy divided by r, and then plus the derivative of v with respect to theta times x squared minus y squared divided by r squared, right? Okay. So with this, what we can do now is to use the previous result that we found to substitute that into maybe this element over here. We have the derivative of u with respect to r, but we know that that is equal to 1 divided by r, the derivative of v with respect to theta times x squared minus y squared divided by r, right? So it is easily noticed that, well, this element is equal to this element over here, right? So we can cancel them. And then we get that the derivative of u with respect to theta times, well, minus 2xy divided by r squared is equal to the derivative of v with respect to r, 2xy divided by r. And then we cancel 2xy, this r squared with this r, to get that the derivative of u with respect to theta is equal to, well, minus r, the derivative of v with respect to r. And this is the second Cauchy-Riemann equation in polar coordinates. Notice that we have also a change of sign, like in the equations for Cartesian coordinates, right? We have that here, we have a plus sign in both derivatives in the equation, but here we need to use this minus sign for the second derivative, right? But in this case, well, it happens something similar, right? For the first equation, there is no change of sign, but in this one, we need to take this minus sign over here. And recall that to keep the same units on both sides of the equation, we multiply r times the derivative of b with respect to r, so that the dimensions of r cancel the dimensions of these r at the denominator. Yeah, so this is like a quick trick to remember where to put the r in the equation. Okay, perfect. So I think that with these two results, I'm going to finish the lesson. Thank you so much for watching.